circles. I mean, they look pretty simple, don't they? Just a round line. But what if I told you that inside that simple shape, there's a whole world of elegant, hidden rules? Rules that actually explain everything from how a bike wheel is built to the way planets orbit. Well, today, we're going to pull back the curtain and decode those secrets, visually.
So let's just dive right in. We're going to use these visuals to uncover all those cool rules. And, by the time we're done here, you're going to see how every single line and every angle inside a circle connects in this, surprisingly perfect way.
But hey, before we can unlock any secrets, we got to know the key players, right? So first things first, let's meet the fundamental building blocks of the circle.
Okay, meet the chord. It's really just any straight line that connects two different points on the edge of a circle. Think of it like this. You're standing on one side of a round park, and you want to get to the other. The chord is your shortcut, that straight path across the grass.
Now, here's where it starts to get interesting. So, what do you think happens when we start moving that chord closer to the center of the park? Well, you can see it right there. It gets longer and longer. This simple, kind of intuitive idea is actually one of the first keys to understanding how circles work.
And that brings us to the king of all chords, the diameter. It is the longest possible chord you can draw, period. And why? Because it's the one special chord that slices right through the exact center of the circle. It's the ultimate shortcut.
Okay, so how do these things all connect? Well, here is your first power-up rule. It's pretty cool. If you draw a line from the center of the circle straight down to a chord so it makes a perfect 90-degree angle, it will always slice that chord into two perfectly equal halves. It's a beautiful example of the circle's built-in symmetry.
All right, so we've talked about the lines inside the circle. Now let's shift our focus to the edge, the circumference, and figure out how we actually talk about and measure pieces of the circle itself.
So, an arc is just a piece of the circle's edge, a section of the crust, if you will. But here's the twist. We don't measure its length in inches or centimeters. Nope, we measure it in degrees, just like a slice of a 360-degree pizza.
So, how do we measure that slice? We use something called a central angle, and you can see why it's got that name, right? Its vertex, its corner, is sitting right at the very center of the circle, and its two arms reach out and basically intercept or grab a piece of the edge, and that piece is our arc.
This brings us to one of the absolute cleanest and, honestly, most satisfying rules in all of geometry. It's simple, it's direct, there are no tricks. The size of that central angle is exactly the same as the size of the arc it creates. Yep, it is that direct. If that central angle is, say, 80 degrees, then the arc it's carving out is also 80 degrees. It's a perfect one-to-one deal. What you see in the center is exactly what you get on the edge. Simple as that.
Okay, that was easy enough. But what happens if we take that angle's vertex, its corner, and we move it away from the center? Like, what if we slide it all the way out to the edge of the circle itself?
Well, then you get this, an inscribed angle. Just look at how its vertex is moved. It's not in the center anymore. It's right on the circle. It's still carving out an arc for sure, but that new position, well, it changes everything.
And this is the big secret. This change in perspective totally changes the math. The relationship is not one-to-one anymore. An inscribed angle is always exactly half the measure of the arc it intercepts. So if the arc is, say, 100 degrees, the inscribed angle looking at it is only 50. So let's put them side by side to really see it. On the left, you've got your central angle. On the right, the inscribed angle. Now look closely. They are both looking at the exact same arc. But because their starting points are different, their measurements are going to be different. And this chart just lays it all out, plain and simple. The central angle, its vertex is at the center, and the angle equals the arc. The inscribed angle, its vertex is on the circle, and the angle is half the arc. So what's the big takeaway here? It's that in a circle, location is everything.
Phew, okay. We have covered a lot of ground, right? We've gone from chords to central angles to inscribed angles. So now let's bring it all home with one last kind of elegant rule and then a super quick recap.
All right, here's one more cool trick for your toolkit. If you take two parallel lines, like railroad tracks, and you slice them through a circle, the arcs that get trapped between those lines will always be equal. It's just another beautiful piece of symmetry that's always hiding inside every circle.
So, let's do a rapid-fire recap. What did we learn? You know that a line from the center that's perpendicular to a chord cuts it in half. You know central angles equal their arcs.
You know inscribed angles are half their arcs, and you know that parallel lines trap equal arcs between them. See? It's not about memorizing a bunch of random rules, it's about seeing the logic.
And really, that's the whole goal here. Once you learn to see these patterns and relationships inside a circle, it stops being this confusing shape and it starts making this beautiful, logical sense.
So now the real question is for you. You've got the rules. Where are you going to spot these patterns out in the world?